Chapter 14, Kinetics. Exercise 14.55. The tabulated data show the concentration of cyclobutane, carbon 4, hydrogen 8 versus time for this reaction. Part A. Determine the order of the reaction. So we will just plot this time and the concentration here. Alright, time in second and concentration in molar. I'm using A for the reactant, and let's have a rough idea about how the concentration changes. So I'm going to select all the data and then insert and then choose scattered, and we can see this is not completely linear, so it's not zeroth order reaction. If you have a zeroth order reaction, well, the concentration of A should decrease in a straight line. This is not straight, so I'm guessing it's first order or second order. I'm gonna delete this, and then if the natural logarithm of A is linear with time, and then that's gonna be first order. Alright, if we plot 1 over A versus time, and if this is linear, we get second order. We'll see. Alright, we'll make two graphs and see which one is more linear. The first one, ln A versus T. Alright, I'll put ln A here. The natural logarithm of A, and I'm gonna just use the equation, embed it in Excel, drag it down, click the bottom right corner and drag it down. Alright, and then I'm gonna plot ln A versus time. This is my horizontal axis, this is my vertical axis. Insert, and yeah, it looks linear. And then we're at the trend line, so don't check this yet, just click the arrow, more options. Now let's choose linear, display the equation. Let's make the equation a little bigger. Click home, font size, make it maybe 12. It's large enough, and you can see r squared is 1. You can see the data is following a linear trend. We have a linear equation with a slope and intercept. We have r squared is equal to 1. This indicates perfect fitting. I think it's gonna be just first order, but just to make this more convincing, let's do the second order as well. To do the second order, we need so this is first order fitting. Alright, this is first order fitting, and then we'll do the second order fitting. Alright, this time we need 1 over A, so this equation will be given to you in the exam, but you need to know how to analyze data. Equals 1 divided by A over here, and we'll drag it down all the way to the bottom. Oh, I did something wrong here. 1 divided by this cell B2, and then we drag it down. Alright, so this is the reciprocal of this, and then we plot 1 over A versus T with time as the horizontal, 1 over A as the vertical. Insert. Well, apparently this is not as linear. Alright, this is second order fitting. Alright, I didn't label the horizontal axis and vertical axis because I just want to finish tackling this problem as soon as I can. Now let's do this trend line and more options. I'm gonna try linear again. This is second order fitting. If it's a second order reaction, well, always should be linear with time. All right. Well, apparently it's not as linear as this one, and r squared is less than 1. So I would say this reaction is first order, not second order, because this is not quite as linear as this one. So this one looks better. Now we're gonna choose first order here. N equals 1, first order. Let's look at part B. Determine the value of the rate constant. This part is easy. The reaction rate constant can be determined using this equation because this is first order. Alright, first order. We know it's first order, and of course K is gonna be R divided by A. So what we're gonna do is we're gonna choose we're gonna compute R and then divide it by the concentration of A. So how do we get R? One way is to just take the difference between these two, divide by 10 seconds, we get R. Alright, and then divide by A. A, I can just use the average of these two values. So let's try it. Let's try it. So K is the reaction rate. This is the change divided by 10 seconds. That's going to be the reaction rate. And then divided by A, we have two values of A. So I'm going to use the average. Alright, I'm going to use the average here. 1 plus 0. Or maybe just average. Let's see if it's going to work. Oh. Okay, somehow I clicked something that I should not click. Alright, oh, I see. I should not put K here. It's just this average. Average. We have B2 and B3. B2 and B3. Alright, that's it. Oh. Okay. Yeah, we got this reaction rate 0.0112. Let's take a look. 0.0112. The unit is per second. There's another way to get the reaction rate constant, which is faster, just by looking at this graph. Alright, just by looking at this graph. If you plot the natural logarithm of A, so I'm going to actually add this L1 A here, just to be clear, versus 1 over time. This is 1 over time. The slope is negative K. So over here, negative 0.0112 is negative K. And therefore, K is positive 0.0112. Alright, so there's another way to do this. Or you can just pick any other two data points. I don't know which two data points you like. I'm going to pick two that are close to each other because I'm about to take the average here. I'm going to use this two. I'm going to use this two. These two data points. 0.326 minus minus 0.364. So this two data point from 90 seconds to 100 seconds, we need a negative sign here because this is the consumption rate divided by 10 seconds. That's the time interval, and over here we need to use B11 and B12 as the concentration. Let's see, 0.011. Well, it's pretty close. Alright, it's still pretty close. The best way to get the rate constant is to use all the data. That means you need to plot the natural logarithm of the concentration of A versus 1 over time. You will get this linear equation for a first order reaction. The slope is negative K. So K is negative slope. That's how we tackle part B. Part C. What's the rate of reaction when the concentration is this. This is really simple because the reaction rate is K times the concentration to the power of 1 for a first order reaction. And we have K here. We have this 0.0112. So we can use Excel to do the calculation. Alright, that's K multiplied by the concentration. The concentration is given to us in part C. It's 0.27, so just 0.27, and that's it. We're done. We get the reaction rate 0.00302. I think you're gonna see that number here, 0.00303. Some rounding error, but it's not important. It's not important. Yeah, same calculation. I think it's pretty weird that they got 3.03 times 10 to the power of -3. Not sure what's going on. Let's do this again. 0.112 times 0.27. Oh, and also there's a typo here. They missed a 0 here. The reaction rate constant should be 0.00112. So let's take a look. Yeah, 0.0112. So occasionally you find a mistake here and there in mastering chemistry. All right, so there should be a 0 here right after the decimal point, and I got 0.00302 instead of 0.00303.